Welcome to the peaceful space of sleep-friendly science, where tonight we'll turn our gaze to the distant, twinkling lights of the night sky and ponder their eternal dance against the vast, dark canvas of the cosmos. Tonight, we gently explore a profound question. In a universe that is constantly stretching outwards, can stars, these brilliant beacons of light, truly live forever? Let your curiosity float freely as we consider the ultimate fate of these celestial giants, drifting together through theories of stellar evolution and cosmic endings. Now, settle in, take a deep breath, and let the soft sounds guide you as we begin tonight's journey into the unknown. Section 1. The stellar cradle's gentle hum. Let your mind drift now, away from the solid ground beneath you, away from the familiar weight of your own body. We are journeying outwards, not with the force of a rocket, but with the quiet intention of a dream. We travel past the moon, a silent, silver companion, past the fiery heart of Mars and the swirling storms of Jupiter. We leave our solar system behind, a tiny, precious jewel of light and life, shrinking in the rearview mirror of our imagination. Our destination lies further still, in a place that seems, at first, like a profound and absolute emptiness. Here, between the established constellations, in the great dark gulfs of the Milky Way, lies a different kind of darkness. It is not empty, it is waiting. Imagine you are floating in this immense expanse. The darkness here is not a void, but a velvet curtain, woven from threads of hydrogen gas and fine, crystalline dust, the frost of ancient, long-dead stars. This is a molecular cloud, a stellar nursery, a cosmic cradle. It is vast beyond comprehension, stretching for light years, so diffuse that if you were truly here, you would feel nothing. But with the senses of your mind, you can perceive it. You can feel the deep, abiding cold, a stillness that has held for millions of years. There is a sound here, but it is not a sound for the ears. It is a hum, a vibration that resonates in the very fabric of space-time. It is the gentle, patient thrum of gravity. For now, this cloud is in a state of delicate balance. The outward push of its own faint warmth, the gentle motion of its particles, keeps it from collapsing. It is a vast, quiet breath, held in cosmic suspension. The dust motes, coated in ice, glint like scattered diamonds in a light that has yet to be born. The hydrogen atoms, the simplest and most ancient of building blocks, drift in a slow, aimless ballet. They are the potential. They are the memory of the Big Bang and the promise of future suns. But nothing in the universe remains static forever. The hum of gravity is a patient shepherd. It never sleeps. It never ceases its soft, insistent call. Perhaps a distant supernova, the explosive death of a giant star, sends a shockwave rippling through this peaceful expanse, like a stone tossed into a still, dark lake. Or perhaps, through sheer chance, a small region within the cloud becomes just a fraction more dense than the space around it. It doesn't take much. A few thousand extra atoms here, a few more grains of dust there. A tiny, insignificant knot in the vast, smooth fabric. But for gravity, this is an invitation. The whisper begins. Gravity's pull, infinitesimally stronger in this small pocket, begins to draw more material in. It is the slowest gathering you can imagine. An atom from a light year away might take 1,000,000 years to answer the call, drifting inward on an unhurried, inevitable tide. It's a process of cosmic accretion, a gentle gravitational waltz. The clump grows, not like a snowball rolling down a hill, but like a drop of dew forming on a leaf in the quiet of dawn, slowly pulling moisture from the air around it. As this central clump, this stellar embryo, grows more massive, its voice grows stronger. Its gravitational whisper becomes a steady murmur, then a resonant call, pulling in gas and dust from further and further away. The cloud, once a single, diffuse entity, begins to fragment, breaking into smaller, swirling eddies, each one a potential birthplace for a star. Let us focus on just one. Here, in the heart of this collapsing knot of gas, a change is beginning to occur. The immense pressure from the infalling material, a weight of trillions upon trillions of tons, starts to generate heat. It is the same principle as the warmth you feel when you rub your hands together, but on a scale that defies the imagination. The very center of the clump begins to warm up, a faint spark of heat in the absolute cold of deep space. This is the birth of a protostar. It is not yet a star. It does not yet shine with the fire of nuclear fusion. Its light is a different, more subtle kind. It is a dull, thermal glow, the sullen, deep red of a cooling ember, radiating away the intense heat of its own formation. This fledgling sun is still shrouded, a secret kept hidden from the wider universe by the dense blanket of gas and dust still falling in upon it. If you could see it, it would be a diffuse crimson heart beating softly within the dark cosmic womb. As the cloud collapses, it begins to spin. Just as an ice skater pulls in their arms to spin faster, the conservation of angular momentum dictates that this collapsing sphere of gas must rotate with increasing speed. The slow, lazy drift of the initial cloud is concentrated into a dizzying, yet graceful, pirouette. This rotation has a profound effect. It prevents all the material from falling directly onto the protostar. Instead, a vast, flat, rotating disk of gas and dust forms around the protostar's equator. This is the protoplanetary disk, a celestial potter's wheel, spinning out the raw materials for future worlds. Within this swirling disk, tiny dust grains begin to stick together, forming pebbles, then boulders, then the seeds of planets, comets, and asteroids. For now, they are just ghosts of worlds yet to be, circling their dim, red parent in a silent, orbital dance. Feel the peace in this immense creative process. There is no violence here, no rush, just the slow, inexorable laws of physics playing out like a celestial lullaby. The gentle pull, the slow spin, the gradual warming. It is a process of becoming stretched across eons. The universe is in no hurry to build its great lanterns. It takes its time, allowing the dust of ages to gather, to warm, and to dream of the light it will one day become. The protostar continues to grow, siphoning material from the disk and the surrounding envelope of gas. Its core grows hotter and denser. The pressure builds to unimaginable levels. The hydrogen atoms, once drifting freely, are now crushed together so tightly that their natural repulsion is being overcome. They are on the verge of a fundamental transformation. The protostar is like a deep breath being drawn in, a moment of profound tension and potential, held just before the song begins. The cosmos holds its breath, waiting for the spark. The crimson glow intensifies, the heart beats faster, and the stage is set for the most magical moment in the life of a star. Its first luminous breath of nuclear fire. But that moment is not yet upon us. For now, there is only the quiet, glowing promise, adrift in the velvet dark. Section 2. A star's first luminous breath. The pressure in the core of our protostar has now become an almost spiritual force. Imagine the weight of 1,000 Earths all focused on a single point. The temperature, once a mere glow, has climbed relentlessly, from thousands to millions of degrees. The hydrogen atoms in the heart of this celestial body are no longer drifting. They are a seething, incandescent plasma, a storm of bare protons stripped of their electrons, crushed together with an intimacy that defies their very nature. They yearn to repel one another, to fly apart, but gravity's embrace is too strong, too complete. And then it happens. In the very center of this crucible, the temperature reaches a magical threshold, 15 million degrees. At this point, the crush of gravity becomes so immense that it overwhelms the fundamental forces that keep atomic nuclei apart. Two protons, two tiny hearts of hydrogen, are slammed together with such violence that they fuse. They merge. In a process both elegant and profoundly powerful, they undergo a sacred transformation. A new, slightly heavier element is born, deuterium, an isotope of hydrogen. This act of creation is not silent. It is not without consequence. The new, fused particle weighs just a fraction less than the two original protons combined. That minuscule missing mass, an amount so small it seems insignificant, has not vanished. It has been converted, in accordance with the most famous equation in all of science, into a burst of pure energy, a pulse of pure light. A single, high-energy gamma-ray photon is born from this union. This is the moment. This is the star's first breath. Nuclear fusion has begun. The heart of the star has ignited. A furnace has been lit in the center of the void, a self-sustaining fire that will burn for billions, or even trillions of years. That first pulse of energy is joined by another, and another, and another, quadrillions upon quadrillions of times every second. A torrent of light and energy begins to flood outwards from the star's core. But this light, this first message from the star's newly awakened heart, does not travel freely. It begins a journey of its own, one of the most incredible journeys in the cosmos. The core is so dense, so crowded with particles, that a photon cannot travel for more than a few millimeters before it collides with an atom. It is absorbed, and then, a moment later, re-emitted in a completely random direction. Staggers left, then right, then up, then backwards. This is the photon's drunken walk. A single particle of light, born in the fiery core, might take 100,000 years or even longer to finally find its way to the surface. It is a message in a bottle, tossed into an impossibly turbulent sea, slowly, patiently, making its way to the outside world. The light we see from the stars tonight is, in a very real sense, an ancient ghost, the echo of a fusion event that occurred in the time of our earliest human ancestors. As this incredible wave of energy, carried by countless staggering photons, pushes its way outwards, it creates a new force, radiation pressure. It is a gentle but relentless outward push of light. And here, a perfect and beautiful balance is struck. The star is now a stage for a cosmic duel, a celestial truce that will define the rest of its long life. Gravity, the great sculptor, continues its work, trying to crush the star further, to pull every atom into an infinitely dense point. But now there is an opposing champion. The fire of fusion, the outward pressure of the light born in the core, pushes back with equal and opposite force. The inward pull of gravity is perfectly counteracted by the outward push of light. This state is called hydrostatic equilibrium. It is a state of sublime grace. The star ceases to collapse. It stops shrinking. It settles into a stable size, a stable temperature, a stable brightness. It has become a true star. It has joined the main sequence. This is the long, peaceful adulthood of a star. It has found its rhythm, its purpose. It will now spend the next 90% of its existence in this balanced state, steadily and reliably fusing hydrogen into helium in its core. It is like a candle that has been lit and now burns with a calm, unwavering flame. Its song is a single, deep, resonant note, held for an unimaginable stretch of time. The fate of the star, its entire life story, was sealed in that initial moment of its formation. The amount of mass it managed to gather from its parent cloud dictates everything that will follow. If it is a small star with only a fraction of the mass of our own sun, it is a red dwarf. It is cool and dim and incredibly thrifty with its fuel. It sips its hydrogen rather than gulping it. Its fusion process is slow and gentle, a tiny pilot light in the dark. These stars are the great survivors of the cosmos, with lifespans that can stretch into the trillions of years, far, far longer than the current age of the universe. If it is a medium-sized star, like the one we will soon visit, our own sun, it shines with a friendly yellow-white light. It is more generous with its fuel, burning through its hydrogen reserves over a stable, predictable period of about 10 billion years. These are the stars that seem to offer the perfect conditions for life to arise on orbiting worlds, providing a long, stable summer for evolution to work its slow magic. And if the star is a giant, 15, 20, or even 100 times the mass of our sun, its story is one of breathtaking brilliance and fleeting life. It is a blue giant, a blazing, incandescent powerhouse. Its immense mass creates crushing pressures and scorching temperatures in its core. It does not sip its fuel. It devours it. It burns with a furious, white-hot intensity, a rock star of the cosmos, living fast and dying young. But for now, our star, newly born, is simply shining. The remnants of its dusty, placental shroud are being blown away by the force of its new solar wind, a stream of particles flowing from its surface. The protoplanetary disk, that swirling potter's wheel, is now fully illuminated. The light of the parent star warms the tiny, gathering worlds, beginning the long, slow chemistry that might one day lead to oceans and atmospheres, and perhaps even life. The star is no longer a hidden promise. It is a beacon, a lighthouse in the cosmic dark, its steady gleam a testament to the perfect balance struck between the crushing force of gravity and the liberating fire of light. It has found its place in the grand cosmic tapestry, and for now it rests in a state of quiet, luminous peace. Section 3. Our Sun, an anchor in time. Let our journeying mind now turn homeward. From the abstract nursery of stars, let us drift back towards a familiar, life-giving glow. We return to our own celestial neighborhood, to a star so deeply woven into the fabric of our existence that we often forget it is a star at all. We call it the sun. Feel, for a moment, the gentle warmth on your skin on a bright day. That warmth is the end of an ancient story. It is the final, tangible touch of photons that began their journey from the heart of our star thousands of years before the first civilizations arose. That warmth is a direct connection to the cosmic engine, a reminder that we live our lives bathed in the light of our very own personal star. Our sun is a beautiful, average main-sequence star, a yellow dwarf. It is not a furious blue giant, nor a tiny, frugal red dwarf. It is, in many ways, the cosmos's expression of a golden mean. It resides in that perfect middle ground of mass and energy that has allowed it to become a stable, long-lived anchor for the family of planets that circles it. For 4.5 billion years, it has held its post, a constant radiant presence. It is the metronome to which all life on Earth has danced. Its rising and setting is the rhythm of our days. Its steady output of energy is the foundation of the very air we breathe and the food we eat. It is the silent, gravitational heart of our solar system, holding planets, moons, asteroids, and comets in a vast, predictable, orbital embrace. Like the newborn star we just witnessed, our sun exists in that state of perfect, divine tension. Hydrostatic equilibrium. Imagine an unseen, cosmic hand, the hand of gravity, perpetually trying to squeeze the sun into a smaller and smaller ball. This hand is relentless, its grip immensely powerful, born from the sun's own incredible mass over 300,000 times that of our Earth. If this force were unopposed, our star would collapse in an instant. But from its core, a second, equally powerful hand pushes back. This is the hand of light of thermonuclear fire. The ceaseless fusion of hydrogen into helium generates a torrent of energy that radiates outwards, creating a pressure that perfectly resists gravity's clenching fist. These two forces are locked in a silent, eternal promise. For as long as the fire burns, the star will not fall. For as long as gravity holds, the fire will have fuel. It is this balance that makes our sun the reliable, life-sustaining beacon it is. Let us drift, in our minds, past its turbulent surface, with its churning plasma and great, arching solar flares. We sink through the convection zone, where great bubbles of hot gas rise and cool, like a pot of boiling water the size of a world. We drift deeper still, through the radiative zone, where those staggering photons continue their 100,000-year journey. And finally, we arrive at the heart, the core of our sun, a place of 15 million degrees, with pressures over 200 billion times that of Earth's atmosphere. Here, the sun's great work is done. Here, in this unimaginable furnace, the proton-proton chain reaction unfolds with a quiet, steady hum. It is a more gentle process than in the giant stars. It doesn't devour its fuel. It transmutes it with a slow, meticulous grace. Every second, our sun converts about 600 million tons of hydrogen into 596 million tons of helium. That missing 4 million tons of mass equivalent to a small mountainese converted directly into energy. It is the light and heat that will eventually reach us. This process has been happening, second by second, minute by minute, for billions of years. It is a clockwork of such immense scale and reliability that it seems eternal. The sun feels like a permanent fixture in our lives, constant, but it is, like all things, a process. It has a past, a present, and a future. It is a story, and we are living in its long, stable middle chapter. Think of the sun's hydrogen fuel supply as the sand in a vast, cosmic hourglass. At its birth, all the sand was in the top bulb. Now, 4.5 billion years later, the sun is comfortably middle-aged. About half of the hydrogen in its core has been fused into helium. The sand has been steadily flowing. It will continue to flow with this same peaceful rhythm for another 5 billion years. This is an almost impossibly long time from our human perspective. It is a stretch of time so vast that it allows us the luxury of seeing the sun as an immortal parent, a tireless guardian. But the physics are undeniable. The fuel tank is not infinite. The hourglass does have a bottom. Every second that the sun shines, every photon that warms our world, is a particle of its life spent, a grain of sand that has fallen and will not return. For now, this truth carries no threat. It is a distant, philosophical reality. We are living in the golden afternoon of our star's life. It is calm, predictable, and life-giving. Its breath, the solar wind, flows outwards, carving a great bubble in interstellar space known as the heliosphere. This bubble is our home. It shields our solar system from the harsher radiation of the wider galaxy, creating a relatively calm harbor in the cosmic sea. So as you rest, feel the comforting presence of this star, even in the darkness of night. It is on the other side of the world, but its influence is ever present. Its gravity holds our planet in its gentle, curving path. Its legacy is in the oxygen you are breathing, a byproduct of the photosynthesis it powers. The sun is the great, unifying principle of our world, a testament to balance, to the long, slow, and steady burning of a celestial fire. It is an anchor in time, yes, but an anchor attached to a finite chain. And to understand what forever means for a star, we must first understand the stories of those whose chains are much, much shorter. Section 4. The Furious Lives of Blue Giants. Let the comforting, steady warmth of our sun fade into the background of your mind. We must journey out again, far from the calm harbor of our heliosphere, to witness a different kind of stellar existence. We are seeking the titans of the galaxy, the ephemeral kings and queens of the cosmos. Our destination is a place of brilliant, raw, and untamed energy. Imagine, against the familiar velvet blackness, a new light. It is not the gentle yellow-white of our home star. This light is a piercing electric blue. It is so brilliant it almost hurts the mind's eye, a diamond so dazzling it seems to tear a hole in the fabric of space. This is a blue giant star, a celestial powerhouse, a fleeting god of light and heat. To be in the presence of such a star is to feel overwhelmed. The sheer scale is difficult to grasp. These stars are behemoths, 10, 20, 50, sometimes even over 100 times more massive than our sun. They are giants not just in mass, but in size, swelling to diameters many times that of our own star. But their most defining characteristic, the one that seals their fate from the moment of their birth, is their staggering luminosity. A blue giant can shine with the light of 100,000, or even 1,000,000, suns. Why? Why this furious, almost violent brilliance? The answer, as always in the life of a star, lies in the eternal duel between gravity and light. But here, the duel is not a balanced fencing match. It is a battle of titans. The immense mass of a blue giant creates a gravitational force of unimaginable power. The pressure in its core is so extreme that it makes the core of our sun seem like a place of gentle calm. This crushing weight ignites a different kind of stellar furnace. Our sun, in its wisdom, sips its hydrogen fuel through the slow and steady proton-proton chain. It is a process designed for longevity. A blue giant has no time for such subtlety. It is ravenous. In its scorching hot core, where temperatures can exceed 100 million degrees, a far more ferocious fusion process takes over, the CNO cycle. Here, atoms of carbon, nitrogen, and oxygen remnants of previous generations of stars act as catalysts. Think of them not as fuel, but as a master chef's perfectly seasoned cookware, allowing the star to cook hydrogen into helium at a wildly accelerated rate. The energy output is colossal. The star doesn't just burn its fuel. It detonates it in a continuous, controlled, yet frantic explosion. It is this frantic pace that dictates the star's brief, glorious life. If our sun's lifespan is a long, slow-burning candle, a blue giant's life is a brilliant firework. It burns through its vast reserves of hydrogen in a mere fraction of the time. While our sun is destined for a life of 10 billion years, a blue giant is lucky to last 10 million. It is born, it blazes with unparalleled glory, and then, in a cosmic instant, it is gone. Its life is a spectacular flash in the pan of cosmic time. The very energy that makes it so magnificent is also its doom. Its light is not a gentle warmth but a searing blast. Its stellar wind is not a breeze but a constant, violent hurricane, shedding mass into space at a prodigious rate. These stars live in a state of perpetual, barely controlled chaos. They are the sculptors of the most beautiful objects in the night sky. The great, glowing clouds of the Orion Nebula or the Carina Nebula are painted into existence by the ultraviolet light of the blue giants embedded within them, causing the surrounding gas to fluoresce in breathtaking shades of pink and red. But this creative power is also destructive. The fierce radiation and powerful winds from these stars can tear apart the very molecular clouds that might have given birth to other, smaller stars. They are careless, extravagant, and utterly captivating. Their brilliance is a mask for their fragility. They are walking a razor's edge. The outward pressure of their light is so immense that it is almost powerful enough to tear the star apart on its own. They are living in a constant struggle, not just against gravity's inward pull, but against their own explosive nature. So let your mind rest on this image. A star of impossible blue-white light, a beacon of ferocious energy, shining with the power of a million suns. It is surrounded by a halo of its own shed light and gas, illuminating the cosmos for light years in every direction. It seems like the very definition of power, of permanence. But we know the truth. We know that its vast fuel tank is being drained at an unsustainable rate. The furious hum of the CNO cycle in its core is the sound of a clock ticking down with incredible speed. Every brilliant photon it releases is a moment of its life it can never get back. This star is not destined for a quiet retirement. It is not built for the long, slow fade of old age. Its existence is a profound cosmic lesson. The brightest flames burn the fastest. The immense energy required to be a blue giant is a debt that must be paid. And when the hydrogen fuel in its core finally sputters and runs out, the bill will come due. The battle between gravity and light will enter a new, desperate, and world-shattering phase. The star's spectacular life is merely the prelude to an even more spectacular death, a final act that will shake the very foundations of its galactic neighborhood. The stage is being set for a transformation, a swelling of form, and an ending that is not an ending, but a new beginning for the elements themselves. Section 5. The White Dwarf's Fading Ember. Not all stars are destined for the furious, spectacular finale of a blue giant. For the vast majority of stars in the cosmos, including our own sun, the end of life is a far more gentle, graceful, and strangely beautiful affair. It is not a sudden explosion, but a slow, magnificent transformation, a cosmic exhalation that unfolds over millions of years. Let us return our focus to that comfortable, sun-like star, our anchor in time. For 5 billion more years, it will continue its steady, reliable song of hydrogen fusion. But the hourglass of its core is emptying. The day will inevitably come when the last atoms of hydrogen in its central furnace are finally exhausted. The steady hum of fusion, the rhythm that defined its entire life, sputters and falls silent. In that moment, the ancient duel between gravity and light is broken. The outward push of radiation from the core ceases. Gravity, that patient, ever-present force, finally sees its opportunity. With nothing to oppose it, it begins to win. The core of the star, now composed of the inert helium ash from billions of years of fusion, begins to collapse under its own immense weight. But this collapse is not an end. It is a catalyst for the star's next great act. As the helium core contracts and crushes itself, it heats up dramatically, just as air warms in a bicycle pump. The temperature soars. This incredible new heat floods into the layer of gas just outside the Korea shell of fresh, unused hydrogen that was never quite hot enough to ignite before. Now it is, like a dying campfire being fanned back to life. This shell of hydrogen ignites in a furious blaze. This new fire, burning in a shell around the contracting core, is far more intense than the original core fusion ever was. The star's energy output increases enormously. This colossal new wave of outward pressure does something extraordinary. It begins to push the star's outer layers, the vast atmosphere that makes up most of its volume, outwards. The star begins to swell, and swell, and swell. It is a slow, majestic, and silent expansion. Over millions of years, the star leaves its comfortable main sequence life behind. It balloons into a red giant. Its surface, now spread over a much larger area, cools down, shifting its color from a friendly yellow-white to a deep, ominous, and yet beautiful ruddy orange. It becomes a colossal, ethereal lantern in the sky. If this were our sun, its expanding outer layers would reach out with ghostly fingers of plasma. They would consume Mercury. They would vaporize Venus. They might even reach our own Earth, boiling away the oceans and turning our blue planet into a charred, sterile cinder. It is a sobering thought, but it is not an act of malice. It is simply the natural, unavoidable autumn of a star's life. This red giant phase is unstable, a temporary state of grand imbalance. The star is now so vast and diffuse that the gravity at its surface is weak. The intense radiation from the hydrogen-burning shell below creates powerful convulsions within the star. It begins to breathe in great, slow pulses like a slumbering giant. With each cosmic sigh, which can take 100,000 years, it sheds a delicate layer of its being into the void. These layers of gas, rich in the elements the star has spent its life creating, drift away, expanding outwards in a ghostly, spherical shell. This is the star's final, most beautiful gift to the cosmos. As the outer layers drift away, they reveal what lies beneath. The star's tiny, incredibly hot, and now exposed core. This core, which has been contracting and heating all this time, finally reaches a new ignition point. For a brief, final flash of glory, it becomes hot enough to fuse its helium ash into heavier elements, primarily carbon and oxygen. But this fuel source is short-lived. Soon, that fire too will die, for a star of this mass can go no further. Now something magical happens. The tiny, exposed core is a furnace of unimaginable temperature, blazing with intense ultraviolet light. This light streams outwards and strikes the expanding clouds of gas that the star just shed. The light energizes the atoms in the cloud, causing them to glow with brilliant colors just as a neon sign glows when electricity passes through it. The result is one of the most sublime and beautiful objects in the universe, a planetary nebula. The name is a historical mistake. It has nothing to do with planets. They are the celestial ghosts of dying stars. Imagine a cosmic butterfly, its wings painted in ethereal shades of ruby red from glowing hydrogen, and ghostly blues and greens from glowing oxygen. At its center, a single, tiny point of light, the star's dying heart, illuminates the entire magnificent structure. It is the star's final artwork, painted on the canvas of space with the very elements it once held inside. This beautiful apparition is fleeting. Over just a few tens of thousands of years, the glowing gas of the planetary nebula will expand and dissipate, growing ever fainter like a smoke ring dissolving into the air. It returns its precious, life-giving elements to the interstellar medium, enriching the cosmic cloud from which new stars and new planets will one day be born. And what is left behind? What remains when the ghost has faded? The core, a white dwarf. This is the final state of our sun-like star. It is an object of profound extremes. It contains about half the mass of the original star, but it has been crushed by gravity into a sphere no larger than the Earth. The density is staggering. A single teaspoon of this white dwarf material would weigh as much as a car. Its atoms are squeezed together so tightly that they have entered a state of matter unknown on Earth, called electron degeneracy. This state, this quantum mechanical resistance of electrons to being squeezed any further, is the only thing now holding the star up against the final, complete victory of gravity. And this white dwarf, it no longer shines with the fire of fusion. The furnace is out. It is no longer a living star creating new light. It is a stellar ember. Its brilliant white light is simply its leftover heat, the residual warmth from a life of thermonuclear passion. It is a memory of light. It will now begin the longest, slowest, and most peaceful process in the cosmos, the process of cooling. With no energy source, it will radiate its remaining heat into the cold of space for trillions upon trillions of years, longer than the universe has yet existed. It will slowly fade from white to yellow to orange to red. Eventually, after an almost infinite amount of time, it will radiate away its last bit of warmth and become a black dwarf, a cold, dead, crystal heart of carbon and oxygen drifting silently and invisibly through the eternal dark. A diamond in the graveyard of the cosmos. This is not a violent death. It is a graceful retirement. It is a giving back. It is a slow, cosmic exhalation that will last for an eternity. Section 6. A supernova's generous legacy. The graceful, fading ember of the white dwarf is a story of peaceful retirement, of a slow and dignified exhale. It is the story of the many. But for the titans, for the brilliant blue giants we witnessed living their fast and furious lives, the end is not a sigh. It is a roar. It is the most violent and consequential event in the universe since the Big Bang itself. It is a death that seeds new life across the galaxy. It is a supernova. Let us return our gaze to that massive star. Its brief 10-million-year life of burning hydrogen is over. Like the smaller star, its core is now silent, and gravity begins its inevitable conquest, crushing the helium ash at the center. The core collapses and heats, igniting a shell of hydrogen around it. The star swells, but not into a gentle red giant. It becomes a colossal red supergiant, a star so vast it could easily swallow the orbit of Jupiter. But this is just the beginning of its frantic, final stand against gravity. As the helium core continues to collapse, it becomes hot and dense enough to ignite. The star begins to fuse helium into carbon. For a time, this new fire provides a reprieve, pushing back against gravity's crush. But the helium fuel burns far faster than the hydrogen did. Soon, the helium is exhausted, leaving a core of carbon and oxygen. And gravity attacks again. The star is now a desperate alchemist fighting for its life. The carbon core collapses, becomes hotter and denser until it, too, ignites, fusing into heavier elements like neon and magnesium. This creates a new, temporary fire, a new line of defense. But this fire is even more short-lived. This process repeats, again and again, in a frantic, accelerating cascade. Each new fuel source is heavier, and each burns for a shorter and shorter time. Hydrogen burned for millions of years. Helium burned for hundreds of thousands. Carbon might burn for only a few hundred years. Oxygen for a year. The final stage, the fusion of silicon into iron, may last for only a single day. The star has developed a layered, onion-like structure in its core. At the center is the newest, heaviest ash. Surrounding that is a shell where the previous element is still fusing. Around that, another shell and another. A shell of silicon fusing to iron. A shell of oxygen fusing to neon. A shell of carbon, a shell of helium, and finally, on the very outside, the last shell of hydrogen still burning with its ancient fire. The star is fighting a war on multiple fronts. But it is a war it is destined to lose. The final stage is the creation of iron. And with iron, the alchemy ends. It is a cosmic dead end. For all the elements leading up to it, the act of fusion off squeezing atoms together releases energy. It is this released energy that holds the star up. But iron is different. Iron is the most stable atomic nucleus. To fuse iron into something heavier, you don't get energy out. You have to put energy in. The core of the star, after a day of furiously creating iron, is now a dead weight. It is a ball of stellar ash that can no longer produce any energy to fight against gravity. The fire doesn't just go out. It becomes a fire extinguisher. The star's internal support system is instantly, catastrophically switched off. What follows is one of the most sudden and violent events imaginable. Gravity, the patient victor, now has no opposition. In less than a single second, the iron core, an object larger than our Earth but containing the mass of 1.5 suns, collapses in on itself. The outer parts of the core rush inwards at nearly a quarter of the speed of light. It is a fall of such unimaginable speed and force that it is almost beyond comprehension. The core collapses until it is crushed past the point of being atoms. Protons and electrons are slammed together with such violence that they merge, forming a sea of pure neutrons. The entire core, once the size of a planet, is squeezed into a ball of neutronium no bigger than a city, perhaps only 20 kilometers across. It is an object so dense that a thimbleful would weigh 1 billion tons. This is a protoneutron star. It is the hardest, densest object the universe can create. and the rest of the collapsing core, still falling inwards at incredible speed, slams into this newly formed, unyielding surface. The result is a cosmic rebound of epic proportions. The infalling material bounces off the neutron core, creating a shockwave of unimaginable power. This shockwave is the star's final, thunderous cry. It begins to blast its way back outwards through the star's own layered, onion-like structure. It is a wave of pure, destructive energy, and as it tears through the star, it does something miraculous. The energy in this shockwave is so immense that it finally does what the star's core never could. It provides the power needed to fuse iron into even heavier elements. As the shockwave rips through the layers, it becomes a traveling forge, a furnace of creation. In these few, violent seconds, all the naturally occurring elements in the universe heavier than iron are born. The gold in a wedding ring, the silver in a photograph, the mercury in a thermometer, the uranium that powers a nuclear reactor, the iodine that is essential for life. Every single atom of these precious, heavy elements was forged in the heart of a dying, exploding star. They are a gift to the cosmos, paid for with the star's life. The shockwave finally reaches the surface of the red supergiant. The star explodes. It is a Type II supernova. For a few weeks, the single, exploding star can outshine its entire home galaxy, a light brighter than 100 billion suns. It is a beacon visible across millions of light years, a final, defiant blaze of glory. What is left behind this spectacular event? Two things. First, an expanding, glowing, and incredibly beautiful cloud of gas and dust. This is the supernova remnant. It is a celestial wreath laid upon the star's grave, rich with all the elements the star created in its life and forged in its death. This cloud will expand for thousands of years, mixing with the interstellar medium, enriching it with the heavy elements necessary for new kinds of worlds and new kinds of life. The calcium in your bones and the iron in your blood were forged in a supernova and scattered across space, eventually finding their way to our nascent solar system to become part of the Earth and ultimately part of you. And at the very center of this expanding cloud, hidden in the glowing mists, is the heart that remains, that tiny, spinning, ultra-dense neutron star. The ghost of the giant that once was. The supernova is not an end. It is the most generous act in the cosmos. It is a violent, necessary sacrifice. The death of one so that countless others may have the chance to be. Section 7. The ever-stretching cosmic canvas. We have lingered in the aftermath of the supernova, our minds filled with the image of its beautiful, expanding remnant, a ghostly cloud of creation. For a moment, let us allow our perspective to pull back, to zoom out from this single dramatic event. We pull back from the swirling nebula, past the neighboring stars. We pull back further, until the entire spiral arm of the galaxy is visible, a river of 100 billion suns. Further still, until our own Milky Way is but one of countless islands of light, adrift in a sea of profound darkness. For most of our journey, we have treated this darkness as a static stage, a fixed and silent backdrop upon which the drama of stellar lives unfolds. We have treated space as a great, unchanging container. But in the early 20th century, humanity made a discovery that forever altered our understanding of this stage. It revealed that the stage itself is part of the performance. The very fabric of the cosmos is not still. It is alive with a deep, silent, and inexorable motion. Imagine yourself now not as a traveler moving through space, but as a still point of observation watching the great archipelago of galaxies. For a long time, we believed these island universes were either stationary or moving about randomly like bees in a swarm. But when we looked closely at their light, we found something astonishing. A universal pattern. With very few exceptions, every distant galaxy is moving away from us. And the further away a galaxy is, the faster it appears to be receding. This was not a cosmic exodus, as if our own galaxy had some cosmic plague. The same observation would be true from any other galaxy. An observer in the Andromeda galaxy would see the Milky Way rushing away from it. An observer in a galaxy a billion light-years away would see all of its neighbors rushing away from it, too. There is only one way to explain this. It is not that the galaxies are flying through space like ships on an ocean. It is that the ocean of space itself is swelling. The very canvas of the cosmos is stretching. Let us use a simple, gentle analogy. Imagine a vast, dark sheet of rubber. On this sheet, we place 1,000 tiny, glowing beads, each representing a galaxy. Now, imagine unseen hands begin to pull at the edges of this rubber sheet, stretching it slowly and uniformly in all directions. What would you see if you were sitting on one of those beads? You would see all the other beads moving away from you. The bead right next to you would seem to move away slowly. A bead on the far side of the sheet would seem to be racing away at high speed. They aren't rolling or sliding. The space between them is simply growing. This is the expanding universe. It is a concept so profound it borders on the mystical, yet it is the physical reality of the cosmos we inhabit. The universe is getting bigger every single second. The deep, silent hum we felt in the stellar nursery was not just gravity, it is also this, the soundless stretch of space-time itself. For a long time, it was thought this expansion might be slowing down, that the collective gravity of all the galaxies might eventually act as a brake, perhaps even pulling everything back together in a distant future big crunch. It was a comforting idea, a cosmic inhale following a long exhale. But in the twilight years of the 20th century, another, even more mysterious discovery was made. The expansion is not slowing down. It is speeding up. Something is pushing everything apart. There is a gentle, persistent, and utterly mysterious pressure inherent in the fabric of space itself. We do not know what it is. We call it dark energy, a name that reflects our profound ignorance more than our understanding. It acts like a kind of anti-gravity, a whisper in the void that says further apart, further apart. It is a force that does not weaken with distance. It is constant everywhere, woven into the vacuum. And because the universe is getting bigger, there's more everywhere for it to act upon. The more space there is, the stronger its overall effect becomes. This accelerating expansion is the ultimate context for our question. Can stars live forever? Because it changes the very nature of forever. It rewrites the destiny of the cosmos. Think of what this endless stretching means. Galaxies, those great islands of stars, are being carried away from each other on an ever-quickening tide. Over unimaginable timescales, our neighboring galaxies will recede from view. First, their light will be stretched, its color shifting towards the red end of the spectrum, becoming weary from its long journey across expanding space. Then they will recede so fast that their light can no longer reach us at all. They will cross a cosmic horizon, a point of no return, their light forever lost to us. The night sky, the truly distant future, will be a lonely place. An observer then would look out and see only the stars of our own galaxy. The countless other beacons of light, the evidence of a vast and populated universe, will have vanished, their existence erased from the sky by the relentless stretch of space. The universe will become a place of profound, unbridgeable isolation. But the effects are not just external. This cosmic stretching has implications for the lifeblood of stars themselves. We saw how the supernova generously scattered heavy elements, enriching the interstellar gas from which new stars are born. This is the great cosmic recycling program. The death of one generation provides the raw materials for the next. But in an eternally expanding universe, this recycling becomes less and less efficient. The gas and dust within a galaxy are a finite resource. While some is recycled, much of it gets locked away in long-lived stars, in cold stellar remnants like white dwarfs, or gets blown out of the galaxy altogether. As the universe expands, the overall density of everything drops. The great, cool molecular clouds, those stellar cradles we began our journey in, will become rarer and more diffuse. The raw material for star birth will be spread thinner and thinner. The expansion acts like a slow, cosmic chill, making it ever harder for gravity to gather enough material to spark a new sun. The universe's creative potential, its ability to birth new light, is being diluted by its own growth. So the stage is now set for the final acts of our cosmic drama. We have seen how individual stars are born, how they live, and how they die. But now we see that their individual stories are playing out against a backdrop that is itself changing, stretching, and becoming colder and more dilute. The universe is not a steady state. It is a process heading towards a specific, predictable future. The era of brilliant, plentiful stars, the stelliferous era we are living in now, is itself a fleeting chapter in the much larger book of cosmic time. The canvas is stretching and the paint is beginning to run thin. Section 8, Twilight of the Stelliferous Era. Let your mind drift forward now into a future so deep it humbles the imagination. We are leaving our present epoch far behind. Billions of years have flowed past like moments. Then, tens of billions. Hundreds of billions. We journey onward to the 1 trillion year mark. A million years from now. The universe we find ourselves in is a vastly different place. It is darker, colder, and profoundly quieter. The Great Expansion has continued its relentless work. Our own Milky Way galaxy has long since merged with Andromeda and the other local group galaxies, forming one single, colossal, and now utterly isolated island universe we might call Milkomeda. Beyond its shores, there is nothing. The accelerating expansion of space has carried every other galaxy beyond our cosmic horizon. The sky is no longer filled with the faint, fuzzy patches of distant island universes. There is only the light of our own galaxy set against an endless, perfect black. The age of brilliant, massive stars has long since passed. The furious, dazzling blue giants, with their 10-million-year lifespans, were among the first to go, like brilliant fireworks that lit up the early evening sky. Their final, spectacular supernovas enriched the galaxy. But the gas they returned was never again dense enough to form stars of their own magnificent stature. They are now just a memory, a legend from the universe's fiery youth. Sun-like stars, too, have run their course. Our own sun has completed its red giant phase, puffed off its planetary nebula, and settled into its long, quiet retirement as a cooling white dwarf now glowing with the faint orange light of a dying ember. Billions of generations of similar stars have followed the same path. The galaxy is now littered with these stellar remnants, these compact, fading cores of long-dead suns. The stelliferous era, the star-bearing era, the age we are so privileged to inhabit us in its deepest twilight. The great cycle of star birth and death has ground almost to a halt. The vast, cool clouds of interstellar gas and dust have been almost entirely used up, locked away in stars and their remnants. The galaxy's creative fuel tank is running on empty. Star formation has not ceased entirely, but it has become an exceedingly rare event. Perhaps only once every million years, in some forgotten, dense pocket of the galaxy, a tiny flicker of new light is born. But these are not the suns of our time. They are the last, most modest children of the cosmos. They are the red dwarfs. These are the stars we met briefly at the beginning of our journey, the tiny, dim, and incredibly thrifty ones. They have less than half the mass of our sun, and they are the undisputed masters of longevity. Because of their low mass, the pressure in their cores is gentle. They sip their hydrogen fuel with an almost unbelievable economy. And unlike a sun-like star which only fuses the hydrogen in its core, a red dwarf is fully convective. It's like a pot of soup that is constantly being stirred. Hydrogen from all parts of the star is continuously cycled through the core, meaning it can use almost all of its available fuel, not just a small fraction of it. Their lifespans are not measured in billions of years, but in trillions. 10 trillion years. 20 trillion. Perhaps even longer. They are the final, enduring generation of true stars. So, the universe at the 1 trillion year mark is dominated by them. The sky is not bright and golden, but filled with a dim, ruddy, crimson glow. It is a cosmos lit by the equivalent of a trillion-year-long sunset. These faint red suns are the last campfires in the growing dark, patiently burning through their immense fuel reserves. They are incredibly stable, these ancient stars. They shine with a steady, unwavering light for eons, their slow and steady fusion a quiet defiance against the encroaching emptiness. But even they are not eternal. Their story, too, must have a final chapter. Let us float forward again to an even more distant shore in time. We journey to the 100 trillion year mark. Here, the universe is almost completely dark. One by one, over the last 99 trillion years, the last of the red dwarfs has finally exhausted its hydrogen fuel. Because they are too small to ever get hot enough to fuse helium, their story ends when the hydrogen runs out. There is no red giant phase for them. There is no planetary nebula. They simply go out. They fade from a dim red glow to an invisible blackness, quietly collapsing into a small, dense helium white dwarf. A final, silent ember to join the countless carbon-oxygen white dwarfs that already populate the galaxy. The very last star in the universe has died. The stelliferous era is over. The last light from nuclear fusion has been extinguished. The word star is no longer a description of a present reality, but a term from ancient history. The universe has entered a new, profound, and unimaginably long phase of its existence. There will be no new sunrises, no new stellar births. The cosmic cradles are barren. The great generative cycle is finished. The darkness is absolute. The silence is complete. Is this the end of the story? Is this what it means for stars to not live forever? A universe of cold, dead, stellar corpses drifting aimlessly through an expanding, empty void? Feels like an ending. It feels like a profound and sorrowful silence. But the laws of physics are patient, and there are processes at play that are even slower, even more subtle than the lifespan of a red dwarf. The universe is not dead. It has simply entered a new state of being. The age of light is over. The age of darkness has begun. An era where the only actors left on the stage are the ghosts and remnants of the brilliant stars that came before. And even these ghosts have one final, strange, and almost unbelievable transformation ahead of them. The story is not over yet. Section 9 echoes in the degenerate era. We now float in a time of almost perfect darkness. The 100 trillion year mark has passed. The last red dwarf has sputtered out. The universe has entered what is known as the degenerate era, named for the degenerate matter that constitutes its primary inhabitants, the stellar remnants left behind by the long-dead stars. Let us take a census of this new, dark cosmos. The galaxy, our Milkomeda, is still a great, gravitationally bound island, but it is an island of ghosts. The dominant population consists of white dwarfs, trillions of them. The carbon-oxygen cores of stars like our Sun and the helium cores of the final red dwarfs. They are cold, dark, and invisible, having long since radiated away their last heat to become black dwarfs. They are city-sized diamonds of crystallized carbon and oxygen, silent testaments to a time of light. Also drifting in this eternal night are the neutron stars, the incredibly dense, city-sized remnants of the great supernovas. They, too, are cold and dark, their initial furious spin having decayed over the eons. They are perfect spheres of pure neutrons, monuments to the violent deaths of the ancient giants. And then there are the darkest inhabitants of all, the black holes, stellar mass black holes, born from the collapse of the most massive stars, drift like unseen predators. And at the center of the galaxy, the supermassive black hole that once commanded a swirling disk of light and gas now sits in perfect, silent darkness, its gravitational influence the only sign of its immense presence. It is the quiet, patient monarch of this dead kingdom. The universe is populated by these degenerate objects, along with orphaned planets, cold brown dwarfs, and scattered dust and gas, all orbiting the galactic center in a slow, majestic, and utterly lightless dance. It would be easy to assume this is the final, static state, a cosmic graveyard where nothing ever happens again. But even here, in this profound cold and darkness, two impossibly slow processes are at work, reshaping the cosmos on timescales that make the lives of stars seem like fleeting sparks. The first process is one of celestial housekeeping. Over trillions upon trillions of years, the orbits of these stellar remnants are not perfectly stable. Every now and then, through a chance gravitational interaction, a black dwarf might have its orbit perturbed. It might be flung out of the galaxy entirely, to drift forever in the lonely intergalactic void. Or, more dramatically, it might be sent on a decaying spiral inwards, towards the great supermassive black hole at the galactic center. Imagine this journey. A dead star, a crystal diamond the size of Earth, spending a quadrillion years slowly circling its way towards the galactic heart. As it gets closer, the immense tidal forces of the supermassive black hole would stretch it, shatter it, and finally tear it apart. The material of the long-dead star would form a brief, final accretion disk, a swirling vortex of matter that, for one last, fleeting moment, would heat up and glow. A final, faint whisper of light in the unending darkness, before being swallowed forever. Over countless eons, this process will slowly clean house, with the central black hole growing ever more massive as it consumes the remnants of its children. But there is another, even more profound process at work, one predicted by the strange laws of quantum mechanics. A process that suggests that even the most stable forms of matter are not truly eternal. This is the theory of proton decay. Our understanding of physics suggests that protons, the fundamental building blocks of atomic nuclei, the very particles that make up the white dwarfs and neutron stars, might not be truly stable. They might have an incredibly long but finite lifespan. The theory predicts that, on average, a proton will decay into lighter particles like positrons and photons after an almost unimaginable amount of time. The estimates vary, but a common figure is somewhere around 10 to the power of 36 years. That's a 1 followed by 36 zeros. A number so large that if every star in the visible universe had lived for the entire current age of the universe, it wouldn't even be a fraction of this time. But in the degenerate era, time is all the universe has. So let us drift forward into this impossibly distant future. A black dwarf, a silent crystal sphere, drifts in the dark. Once every few million years, by pure chance, a single proton within one of its carbon atoms decays. A tiny, imperceptible flash of energy is released. The atom is transmuted. Over a timescale of 1036 years, this will happen again and again and again. The stellar remnants, these seemingly eternal monuments, begin to slowly, painstakingly evaporate. Atom by atom, they dissolve back into fundamental particles and radiation. It is the universe's ultimate act of recycling, returning even the most stable matter back to pure energy. The black dwarfs, over these hypereons, will slowly vanish, their crystalline structures dissolving into a faint, diffuse mist of radiation. The neutron stars, those ultra-dense spheres, will suffer the same fate, their neutrons decaying and their immense mass slowly bleeding away into the void. The universe becomes even emptier, even more tenuous. The grand structures of the past stars, planets, remnants are all gone. They have been unmade, their substance returned to a bath of low-energy photons, neutrinos, and other stray particles, all spread impossibly thin by the continued expansion of space. What is left? What can possibly survive this ultimate decay? Only the black holes. They are not made of protons, so they are immune to this decay. They have continued to grow, swallowing any stray matter that came too close. They are the last bastion of structure, the final, massive holdouts in a universe that has dissolved everything else. The degenerate era slowly gives way to the black hole era. The universe is now a vast, dark, and expanding emptiness, populated only by these points of infinite gravity separated by unimaginable distances. Seems now we have surely reached the end. When matter itself dissolves, what more can happen? But even these gravitational champions, these final kings of the cosmos, are subject to a law of physics even more subtle, even more patient than proton decay. They too have a lifespan, and their slow, final evaporation will set the stage for the ultimate fate of everything. Section 10. Heat, Death, and a Final Whisper. We have arrived at the final epoch of time, a period so far in the future that the language of years fails us. We are in the black hole era. The cosmos is an unimaginably vast, cold, and dark expanse, its expansion still accelerating, pulling everything further and further apart. The great galaxies have dissolved. The black dwarfs and neutron stars have evaporated through proton decay. All that remains of structure are the black holes themselves, drifting in sublime isolation. They are the ultimate survivors, the final repositories of mass and information from the vibrant universe that came before. At the center of what was once our galaxy, the supermassive black hole reigns, now swollen with the mass of trillions of consumed stellar remnants. Scattered at immense distances are the smaller, stellar-mass black holes, the ghosts of the ancient blue giants. They seem eternal, their gravitational pull absolute, their nature a perfect trap for light and matter. Nothing, it seems, can touch them. But there is one last, strange, and beautiful piece of physics to consider. A discovery that blends the world of the very large gravity with the world of the very small quantum mechanics. It is the discovery that black holes are not perfectly black. They glow. This glow is not the hot, brilliant light of a star. It is a cold, ethereal, and unbelievably faint radiation. It is called Hawking radiation. At the event horizon of a black hole, the very edge of the abyss, the strange quantum nature of the vacuum allows for pairs of virtual particles to pop into existence for a fleeting moment before annihilating each other. Occasionally, one particle of a pair will fall into the black hole, while the other escapes. To an outside observer, it looks as if the black hole has just emitted a particle. This process is a leak. It is an incredibly, mind-bogglingly slow leak. For the particle that escapes to become a real particle, it must draw its energy from somewhere. And it draws it from the only source available, the mass of the black hole itself. Every time a particle escapes, the black hole loses a microscopic amount of mass. It gets just a tiny bit smaller. It evaporates. The rate of this evaporation is inversely proportional to the black hole's mass. This means that small black holes evaporate faster than large ones. A stellar mass black hole with the mass of a few suns will take an astonishingly long time to evaporate completely. A timescale on the order of 10 to the power of 67 years. A googol years is 10 to the power of 100, so this is a number we can barely write, let alone comprehend. The supermassive black holes with the mass of billions of suns will take even longer. Perhaps 10 to the power of 100 years, a googol years, for the last, most massive black hole in the universe to finally shed its last particle. So let us float in this ultimate future. We watch as, over these final, unimaginable eons, the black holes slowly, gracefully radiate themselves away. They are not eternal after all. They are the longest-lived, but still finite, structures in the cosmos. They are the universe's final, slow exhalation. As a black hole evaporates, it gets smaller and hotter. In its very final second of existence, the evaporation becomes a runaway process and the last of its mass is released in a final, faint flash of gamma rays. A quiet, lonely firework in the eternal dark, a final goodbye from the last structured object in the universe. And then, silence. One by one, across the expanding void, the last black holes wink out of existence. The black hole era ends. We have arrived at the final, theorized state of the universe. The dark era. What is left? A universe larger than we can imagine, still expanding, still getting colder. It is filled with a thin, uniform soup of fundamental particles. A bath of low-energy photons, neutrinos, electrons, and positrons, all separated by vast, unbridgeable distances. There is no structure. There are no objects. There is no memory of stars or galaxies or black holes. The temperature of the universe has approached, for all practical purposes, absolute zero. This is the state known as the heat death of the universe. It is a state of maximum entropy, a state of perfect, peaceful equilibrium. There are no more temperature differences to drive any process. There is no more usable energy. There is no more change. Time itself, which is measured by the progression of events, may lose its meaning. Can stars live forever in the expanding universe? The answer, whispered from the deepest future, is a gentle but definitive no. The story of a star, like the story of the universe itself, is a story of finite resources and finite time. From the slow gathering in the stellar cradle to the brilliant fire of fusion, from the generous death of a supernova to the quiet fading of an ember, every stage is a temporary one. And the universe itself, the great canvas, shares this fate. Its story is one of a brilliant, energetic beginning, a long and creative life, and a slow, graceful slide into a final, quiet peace. An eternal, silent stillness. It is not a sad ending. It is a natural one. The beauty of a star, the beauty of a flower, the beauty of a life is not diminished by its finitude. In fact, it may be amplified. The preciousness of the light is defined by the darkness that surrounds it. The warmth of the fire is made meaningful by the inevitable cold. The vibrant, creative, and beautiful universe we inhabit is a fleeting, glorious moment, a precious, cosmic breath between two eternities of silence. And so, our journey through time and space comes to its gentle close. We have seen the birth of stars and the death of the cosmos itself. We have touched upon the finite beauty of all things. Now, it is time to let these grand, cosmic thoughts dissolve, like sugar in warm water, into the quiet peace of your own mind. Let the vastness of space become the vastness of your own potential for rest. The story is over. Your own night has just begun. Sleep well, sleep deeply, and may your dreams be filled with the quiet, wondrous light of a billion stars. Good night.